All right, today we're going to talk about differential calculus. This is a multi-semester long course that most students take just on differential and integral calculus. I'm just going to teach you enough that you can get by in this course if you're concurrently enrolled in calculus, or if you've taken calculus before and you've forgotten a lot. This will be a nice review of what a derivative is. So a derivative is basically how something changes with respect to something else changes. How does x change as time changes? And a derivative is that in the limit of very, very small changes. So I'm going to take the limit, I've got maybe the position of some object as a function of time. How does its position change per unit time in the limit as that little step in time goes to zero? So infinitely small steps. And these derivatives can be in terms of whatever variable you want. For example, if I have the intensity of light on the ground and I know the intensity changes with position x, I can take a derivative. How does intensity change with respect to x? All right. Now, here's just an example. Let's think about velocity. Velocity is something that most people have some understanding for. So imagine that a car drives from Orem to St. George, a distance of 265 miles. The journey takes 4 hours and 24 minutes. How fast was the car moving in miles per hour? Well, the average velocity is just how far we went divided by how long it took. 256 miles divided by 4.40 hours. So the average velocity on the trip is 60.2 miles per hour. But that's the average for the trip. During the trip, maybe the car slows down or speeds up. Its velocity could be different throughout the trip. For example, imagine this is a plot of the position of the car as a function of time, and it takes 4.4 hours to go the distance, but it's not traveling at the same velocity at every moment in time. Here, the car is just sitting still. Time's going by and its position's not moving. All right, so the velocity of the car is related to the slope. Well, it's equal to the slope of that line, distance per unit time. So the average velocity over some time interval is just how far we went during that time interval divided by that time interval. The instantaneous velocity is the limit as that little step in time goes to zero. I want to know not the average over all of this, time. I want to know exactly how fast is it going at this moment in time. So I take the limit as my time step goes to zero, and that's a derivative. So derivative is changing something per something else, changing something else in the limit of infinitely small steps. Now notice, as dt goes to zero, dx is going to go to zero, but the ratio will not, right? So that in a microsecond, I may move just a micrometer if I'm moving 1 meter per second. So my velocity is finite, 1 meter per second, even though the time step is infinitesimal and therefore the distance step is infinitesimal. So the position of an electron is given by the equation x is equal to 2.12 meters per second cubed times time cubed. That's plotted down here below. So imagine I have an electron and it's moving according to this equation. Let's just imagine that. Find the instantaneous velocity at t equals 1 second by finding the average velocity from t equals 1 second to t equals 1 plus epsilon seconds, and making epsilon smaller and smaller until the velocity doesn't change more than 0.01 meters per second. So we're going to find the instantaneous velocity to within an accuracy of 0.01 meters per second. And the way we're going to do that is we're just going to calculate average velocities for smaller and smaller times until that velocity doesn't change anymore. All right, so here's the equation for how my electron's moving, and here's like our definition of a derivative. It's just the limit as delta x and delta t go to zero. So let's let our time step be 0.1 seconds. So the velocity is just going to be how far we are at 1.1 seconds minus how far we were at 1 second. So x evaluated at 1.1 seconds minus x evaluated at 1 second. And here's x again. And that's our change in position. And then I just divide by the change in time, which is 0.1 seconds. Well, if I evaluate this equation at 1.1 seconds, I get this. At 1 second, I get this. And so I calculate and I find that the electron is moving at 7.0 0.172 meters per second. And that is the average velocity over that time interval. But what if we make the time interval smaller? Let's go from 1 second to 1.01 seconds. So our time interval is just 0.01 seconds. When I do that, I plug these times into my equation. I get my values for x at those different times, take the difference, divide by the time change, and that's how fast I'm moving on average over that 0.01 seconds. Let's drop our time down to 0.001 seconds. And when I do that, I find that's my average velocity from 1 second to 1.001 seconds. Okay, so it's still changing significantly. So let's add some more zeros. 0.001, a tenth of a millisecond, 100 microseconds. Plug in the numbers, there's the instantaneous velocity. Let's add another zero. We're going from 1 second to 1.00001 seconds. Plug in the numbers, and you see the velocity did not change to like 4 decimal places, so probably to 4 significant digits. So probably to 3 significant digits, the velocity is 6.36. But maybe, it keeps changing just a little bit. Plus, this is a very tedious thing to do. This doesn't seem like a good way to calculate instantaneous velocities. So that's where the derivative comes in. But before we talk about how to calculate a derivative, let's build some intuition. So let's imagine I have a car and it's moving according to this graph right here. So here's the position it is on the road versus time. All right, so it's going forward, but then it turns around, starts going backwards, and eventually it passes where it started and goes in the negative direction. Now, at what times is it moving forward? So when the value is positive, that just means that the car is to the right of its starting location. It doesn't tell us anything about what direction it's going. The direction it's going depends on the slope, right? So when the slope is downward, the car is moving in the negative direction. When the slope is upwards, it's moving in the positive direction. All right? What times is the car moving quickly? At what times is it moving slowly? At what times is it stopped? Well, here the slope is fairly high, so the car is moving forward fairly quickly. Right here, the slope is still upward, but it's more shallow. So there it's moving forward, but slower. Right here, where the slope is 0, the car is not moving. Then it starts moving backwards. And right here, it's moving backwards fairly quickly. Right here, it's moving backwards, but not as quickly because the slope is not as sharp. Right here, it's almost at a stop. Looks like it's barely creeping forward, and then it starts to move in the negative direction with a negative velocity. Now, at what times is its velocity increasing? Well, if the velocity is the slope, how is the slope changing? Well, here the slope is getting smaller. So right now the velocity is decreasing. It's still decreasing. The magnitude is increasing, but it's increasing in the negative direction. So I'm going to call that a decrease in velocity. All right. Now, if I take the derivative of this function, which gives the position of the car, the derivative with respect to time is the velocity, and that's plotted here in red, right? Where the slope is positive, that's the velocity being positive. Where the slope is 0, that's when the velocity goes to 0, all right? Where the slope is very sharp downward, that's when we have a big negative velocity. Right here, I said it was just looks like there's a slight upward slant. It's moving very slowly forward, and that's what we see when we plot the derivative of position, which is velocity. Right here, it's positive velocity, just barely positive. So what times is it going slow? When the red curve is close to 0, like right here, it's moving very slow. Right here, it comes to a stop, and so forth. When is the velocity decreasing? When's it increasing? We said here it was decreasing because the slope is going down. And if I take the derivative, I see, the velocity is going down, right? And then here the velocity is going up, right? The velocity is still negative, but it is decreasingly negative. It's increasing in positive words. Now, if I take the derivative of velocity, I get this green curve here, which is the acceleration. Look right here, the position of the car is 0. Its velocity is positive, but the slope is constant, so the velocity is not changing. So the slope of the velocity is 0, which means the acceleration is 0, and so forth. All right, so there's some intuition on derivatives using velocity as the thing we were examining. Let's think of some simple derivatives. Imagine that I have a function which is just a constant. As a function of time, x is constant. That would be zero velocity, right? It's not moving. So the derivative of a constant is just zero. Now let's imagine a straight line. X is equal to c times t, all right? The slope of that line is just c, so the derivative of that is just c. So the velocity of my car, if the car is traveling such that x is equal to c times t, its velocity at all times is just c. It's just the slope of the line. So the derivative of a constant times t is just the constant. How about t squared? Oh, if I plot that, that's a parabola. The slope is changing with time. It's zero at time t equals zero, and then it increases with time. It turns out the derivative of c times t squared is just 2c times t. All right? In general, the derivative of a constant times my variable I'm taking the derivative with respect to the nth power is just n times c times that variable to the n minus 1 power. And it doesn't matter what that variable is. It could be t. So ddt of ct to the n is nct to the n minus 1. That could be derivative with respect to z, right? The derivative with respect to z of c times z to the nth is equal to n times c times z to the n minus 1. Or I could be taking the derivative with respect to smiley face. The derivative with respect to smiley face of a constant times smiley face to the nth power is equal to n times the constant times smiley face to the n minus 1 power. So what is the derivative of 4t cubed with respect to time? Well, it's just t to the third power, so it's going to be 4 times 3 times t to the n minus 1, or 2. There it is. So 12 times t squared is the derivative of 4t cubed with respect to t. All right, now what if I have, here's the equation for a line. It's got a slope, but it's also got the intercept here, right? A constant. Well, the slope of my line doesn't depend on that constant, right? It's just d, right? So I have a slope from this term and no slope from that term. When I add them together, the derivative is just going to be the sum of their slopes. So for example, c plus dt plus gt squared, I look at that and I say, if I take the derivative of that, that's just going to be the derivative of each term I'm adding together. So it's going to be 0 plus d plus 2g times t, right? So here's a technique you should know. The derivative of a function plus another function is just the derivative of the one function plus the derivative of the other function, right? We said the derivative of c plus dt plus gt squared is just the derivative of c plus the derivative of dt plus the derivative of gt squared. So I can break up derivatives of sums and just do the sum of derivatives, right? Another trick you should know is that the derivative of a constant times something is just the constant times the derivative of the something. So constants just can come right out of the derivative. Those are two things you should know about when you do derivatives. All right, so the position of a light gray rock, which is fairly round but chipped on one side, is given by the equation x of t is equal to 4 meters plus 17 meters per second squared times time squared. What is its velocity as a function of time? Well, the velocity is just dx dt, and I take the derivative of each of these terms, the derivative of 4 meters. 4 meters is a constant, so that's 0. Then I take the derivative of 17 meters per second squared times t squared. 17 meters per second squared is a constant, so it just comes through. And then the derivative of t squared is 2 times t. So, all right, the velocity is 34 meters per second squared times t. All right, here's some derivatives you should know. We already talked about x to the n. The derivative of x to the n with respect to x is just n times x to the n minus 1. The derivative of sine of theta with respect to theta is cosine of theta, and the derivative of cosine of theta with respect to theta is negative sine of theta. Those are two you should also memorize and remember because they will be used a lot. And then the derivative of the natural log of x is just equal to 1 over x. That's another one you should remember. All right, another trick you need to know how to do is called the chain rule. The chain rule says that the derivative of f with respect to a is just the derivative of f with respect to b times the derivative of b with respect to a. What is that useful for? Well, for example, imagine I have a thermostat, and as I turn up the knob on the thermostat, the heater puts out more power. And I want to know, how does the power change as I as I change theta, as I rotate the knob? What's the power change per change in that angle? Well, imagine I don't know that, but I do know the change in power per temperature. So my knob has different temperature labels, right? So as I turn my knob from, you know, 70 degrees to 75 degrees, I know how much power that changes in the output of my heater, right? Well, if I know how the power changes with respect to the temperature, and I know how those temperature markings are arranged so that I know that, if I turn 10 degrees uh, of a circle, that changes the temperature by 3 degrees Fahrenheit or something like that, right? So if I know how the power changes with temperature, and I know how the temperature setting changes with theta, then I can find how the power changes with respect to theta, right? It's just, right? It's as if these two dt's just cancel out. Here's another example of using the chain rule. Imagine I want to find the derivative of sine of kx. Well, I know how to find the derivative of sine of x, right? The derivative of sine of x is just cosine. But what about the sine of kx, where k is a constant? That constant's messing everything up. Well, let's do this. Let's define a new variable. Let's define u to be equal to k times x. So now I can write this as the derivative with respect to x of sine of u. Well, that seems more complicated because u depends on x, and I've buried the dependence of x in there. But now I can use the chain rule. I'm going to write the derivative of this with respect to x is just the derivative of it with respect to u times the derivative of u with respect to x. I can do this because d du of sine of u is just cosine of u, and du dx, well, u is just this, right? So du dx is just k. So this is just k times cosine of u, and of course u is kx. So there we go. The derivative of sine kx with respect to x is just k cosine kx. So we were able to do that using the chain rule. Here's another example. Let's say I want to take the derivative of 4x plus 3 all cubed. Well, that looks complicated, but let's just define u to be equal to 4x plus 3. Now, this is just the derivative of u cubed, but it's a derivative with respect to x, and the thing I have is u, so we'll use the chain rule. The derivative with respect to x is just the derivative with respect to u times du dx. Well, the derivative of u cubed with respect to u is just 3u squared, and du dx, this is u over here, du dx is just 4, right? 3 is a constant. The derivative of 4x is just 4. And so it's basically 12u squared, but u is 4x plus 3, so this is 12 times 4x plus 3 squared. That's the chain rule. Another useful thing is the product rule. The derivative of one function times another is just the one function times the derivative of the other, plus the other function times the derivative of the one. So for example, if I wanted to find the derivative of x times sine of kx, that's just x times the derivative of the sine plus sine times the derivative of x. Well, the derivative of sine kx, we just found that using the chain rule. That's k times cosine kx. So I have x times the derivative of the sine, which is k cosine kx, plus sine times the derivative of x with respect to x. The derivative of x with respect to x is 1. X changes by 1 unit for every change of x in 1 unit, right? So the derivative is just kx cosine kx plus sine kx. Another useful thing is the quotient rule, all right? The derivative of f over g is just g times the derivative of f minus f times the derivative of g all over g squared. So the derivative of the natural log of x over sine of kx is just sine of kx times the derivative of the natural log minus the natural log times the derivative of sine all over sine squared. But of course, the derivative of the natural log is just 1 over x, and the derivative of sine is just k times cosine kx, so there is my answer. Now, there's a pattern we use when we take derivatives. First, if we have sums, we break them up, right? So if I'm taking the derivative of a bunch of things added together, I break those up into the sum of individual derivatives of each part. And then for each part, I use the product or quotient rule if needed to simplify the derivative. Then I use the chain rule to make what's left look like something that you know. Pull out any constants, evaluate the derivatives, and then simplify. Now, there's notation that we use. So we've been writing derivatives, right? The derivative of f with respect to x, we've written it as df over dx. That can also be written as d over dx operating on an f. So this one, the first one kind of says, hey, it's a little change in f with respect to x. The second one, it's the exact same thing, but it kind of makes you think about it differently. D dx is an operation I do on this function f. And I like these two notations because, well, this one in particular, because it reminds me that really I'm taking a small change in something as I change something else. Also, it lets me know what I'm taking the derivative with respect to. Maybe f is a function of a bunch of different variables. I'm taking the derivative with respect to x. Now, there's another notation that's commonly used, which is just to put a prime here. So f prime is the first derivative of x, right? It's the derivative, or sorry, it's the derivative of f. But is it the derivative with respect to x or y? I don't know. So if f is a function of one variable, this notation works. If not, it's a little harder to use because you need to know which variable you're taking the derivative with respect to. Also, it de-emphasizes this idea that a derivative is a little change in something divided by a little change in something else. Now, I can take the derivative of a derivative. So let's say I take the derivative of f with respect to x, I get my result, and then I take the derivative of that. That is what we call the second derivative, which we write this way, d squared f over dx squared, or if I want to think of this as an operation, d squared over dx squared operating on f. So this operation right there says take the derivative twice. In this other notation, you would write it as f with two primes, f double prime. I can also take the derivative of the second derivative, and that gives me the third derivative, which would be f triple prime, and so forth. You can take whatever derivative you want, as many derivatives as you want. Now, how do you take the derivative of vectors? Well, if we write our vectors using the unit vector notation, it's really simple because the unit vectors are just constants. So df dq is just derivative of x dq times I hat. I hat's a constant. It just comes through the derivative. Plus dy over dq times j hat, because j hat's a constant. Plus dz over dq times k hat, because k hat's a constant. So for example, if I have some a position of an object r vector, which has an x component, a y component, and a z component, the velocity is just the derivative of position with respect to time, which is just these should be dt's here, sorry, typo, dx dt times I hat plus dy dt times j hat plus dz dt times k hat. So the x component of velocity is just the thing that goes with the I hat, which is dx dt. The y component of velocity is just dy dt, and the z component of velocity is dz dt, which makes sense, right? The z component is how z changes with respect to time. So for example, if my position is given by a constant times t I hat plus a constant j hat minus a constant times t squared k hat, the velocity is just the derivative of that position with respect to time, which would be a times I hat, because a is a constant, the derivative of t is 1. B is a constant, the derivative of a constant is 0. C is a constant, the derivative of t squared is 2 times t, and I can simplify that. There is the velocity of my object if its position as a function of time is given by that. And that's the end of our discussion on derivatives.